Hello everyone, thank you for coming along this afternoon to the seminar given by Dr. Helena Stage, who is a postdoctoral research associate at the University of Manchester, an expert in levy processes. Today she'll be talking to us about a heuristic introduction to the applications of Wiener-Hopf factorisation in random processes. Please take it away.
Thank you. Thanks for having me. Yes, so very subtle branding. I am indeed from Manchester. And so, as Mike said, this is a heuristic introduction to the applications and so on. And I do mean the heuristic part of that title, but I am an applied mathematician and I use levy processes, stochastic processes, and that formulation to work with real-life problems. So what I'm hoping to do today is to give an intuition as to how Wiener-Hopf methods can be applied more generally. So what I want to do is to start motivating that a little bit, and please ask questions. I love questions, so jump in at any time. Just don't do the thing an undergrad did to me last week of throwing chalk at me to get my attention. Walled up paper balls do just as well, so I recommend that instead. But please ask questions. Any questions before I begin? There never are. Okay, right. So, in my mind, Wiener-Hopf is a beautiful method, and I like to think of it simply as a decomposition method for solving some kind of integral equation. That can be part of a stochastic process, and we can think about that very generally. Often that integral is implicit in the expression that we're working with, and sometimes it's explicit. And many of these fall under the umbrella of levy processes, which are the kind of processes that I like to work with. I don't know, show of hands, how many people actually work with levy processes in the room? It's absolutely fine if it's none of you. Okay, good. That's kind of what I was hoping for. So what I want to do is I want to walk you all through a random walk example of how we can use Wiener-Hopf methods to bridge the gap between stochasticity and this method, and hopefully also give you some idea or some motivation as to how you can then use Wiener-Hopf methods to solve any and all of these areas. So these are all things that I do, that I solve problems on at the moment. My two favorite ones are neuronal signaling and human movement, but genuinely stochasticity appears so many different places in real life, in physical phenomena, in finances, in ecology, you name it, there is probably a way of formulating that in a stochastic way that is actually also beneficial, not just an alternative reformulation of a problem that's already known. So hopefully, with this slide, I can at least motivate why you may want to consider using Wiener-Hopf methods, maybe in a bit of a more dirty manner than you usually do, but you'll get ample reward. Well, hopefully I've convinced you that. If not, don't tell me until the end. Okay. So when I say a random walk, the things I think about in that context is I'm interested in a particular event, or I'm interested in the mean of some particular quantity over many realizations of that event. That can be a density, that can be the first time a density reaches a particular value, it can be when the first time a neuron fires, it can be the first time a person arrives at this particular train station after having jumped on a random train when they're doing interrailing. It can be many, many different things. But usually when we're talking about stochastic processes or stochastic modeling, we're interested in one of two quantities. We're either interested in a first passage time, so the first time that via some stochastic process, we reach a particular value. So what's the first time if I randomly move, and I try and find a particular college here in Cambridge, and I move randomly, that I'll find it, given how Cambridge is actually built. Very small chances of that, but in general, that's the kind of question we might ask. Or on the other hand, you're looking at a pair or ladder process where I want to know the value of a particular quantity and the time at which that value is reached simultaneously. And that gets more into the realm of more foreign levy processes, but the idea is exactly the same. On the other hand, something that applies a bit more formally when we look at finance is value variation, so the first time a price of an option perhaps exceeds or falls below a particular preset bound that we have. and you can think instead of price, some particular other quantity you're interested in. As far as I'm concerned, it's just a value. I'm going to call it x, but x can be a position, it can be a price, it can be any space in which you want to move. Is that more or less clear how I'm thinking about these kind of processes? Any questions so far? No questions. Okay, we'll keep going then. So what I want to do is I actually want to motivate Wiener-Hopf methods, and I want to do it by showing you how I think about particular problems that are stochastic in nature, and I'm going to assume you at least have a rough idea of Wiener-Hopf methods. Maybe this is a big assumption, but you've come to a talk on the application of Wiener-Hopf methods, and so what I want to do is I want to go through a calculation of what's called the Sparr-Anderson theorem, and it's a coincidence that he was also Danish. I haven't chosen it for that reason, but he was, and I want to address this particular question. And hopefully those of you who are familiar with Wiener-Hopf will see the many similarities, and those of you who aren't will still be able to follow, and you can then go afterwards and see what the similarities are between what I've spoken about and Wiener-Hopf more generally. So the question is, if I start from the origin, and I'm moving, and this can be position space, or money space, or density space, I'm not particularly concerned about that, but let's say moving in discrete time, and we have each time step, how many time steps will it take if I start at the origin to, for the first time, be in the positive domain? Now we can rescale that, obviously, to without loss of generality to any particular point on the x-axis, but that's the question. So a few things to notice about that. That's a first passage problem, so the first time we get into a particular domain, and it's in discrete time. Also, although Sparr-Anderson published something along these lines in '54, Pauli already considered it in the 1920s, although it wasn't quite the same problem. And what we're going to be thinking about fundamentally in addressing this kind of problem is stochastic movement, but when we think of our spatial displacements, we're not going to be moving the same distance each time. My distance is going to be sampled from a distribution, p of x. Okay. Is everyone clear on the problem so far? This is a really good time to ask questions if you have any. No? Okay, because what I want to do now is I actually want to go through that question and answer it with you. So, any questions? Last chance you have.
What kind of journal then? It's journal, I understand, but what's the name?
I don't remember the particular journal. I can look it up for you. I have it on my laptop. If you search polio first passage times, it will definitely come up. It's quite a well-known paper. I was just trying to give you an idea. I don't remember the name. I can let you know. So, I want to go through that calculation, and before doing that, I want to give you a few reminders. I'm sorry if you feel patronized, but just so we're all on the same page here. This is how I define a Fourier transform. So far, so good, hopefully. How many people have worked with generating functions before? Again, I'm sorry if it's patronizing. How many people have? Okay, so this is a useful reminder for some people then. If we think of a Taylor expansion, the coefficients of a Taylor expansion are just going to be constants. The generating function you can think of as being a high-dimensional version of that, where instead of constants, it produces other functions. The characteristic function lambda here is just a Fourier transform of this distribution p of x I said I had before with my step lengths that I'm taking. And then a key quantity we're going to be working with when we think of a random walk is going to be Pn of x. So remember, we're in discrete time, so I have n time steps. So this is my probability as I'm walking through space of being somewhere after those n steps. Okay? Now, where I am at time step n is going to depend on where I was at time step n minus 1, convoluted by all the possible displacements I could have made. And so if we put that into Fourier space, we can use the convolution properties of the Fourier transform, and we can write that in terms of our characteristic function and our initial condition. This is why so many people who think of stochastic processes, they often don't actually work with the probability distributions. You work with the Fourier transforms, because in Fourier space, as you all know, everything is so nice and lovely, and it's just product instead of integrals, so that's fun and good.
But I mean, x is continuous or discrete variable?
X is continuous.
So it's not probability, it's probability density for Pn. Right?
This is, no, so we're going to have a probability density. This is for a particular point x.
But for a particular point, if it's continuous, it's not zero probability, if it's not density. I mean, it's an elementary question, but.
So when you integrate this over all x, you get 1.
Yeah.
Okay.
But when it's density, when it's probability density, no? If you integrate, okay.
No, so no, because at each time, so it's there's a distinction here between where I am and at a particular time step. Given where I was at the previous time step, the probability of me having made a displacement that ends up with me being somewhat, you can think of it as conditional.
Displacement, okay.
Yes, you can think of it as conditional on your previous position. Okay.
So you're thinking continuous in space but discrete in time?
Yes. Any other questions? Okay, I'm going to draw a picture now. Hopefully that will help a little bit. Does anyone else want to have a look at this before I pull the board up and this somehow magically disappears? Okay. So, pretty picture time. That's my favorite time. Let's actually draw this. Oh, I love this. I never had my back. Usually when the balls are fixed, I have to go like this to actually fit it. This is good. Okay, that is, okay, let's imagine that that's a straight line, more or less. And let's say that this is our origin. What we're going to do is we are, as per your question, going to define some probability densities. And in particular, we're going to define those according to what we're trying to find. Is remember, our original question is, what is the probability that after and so many time steps, I arrive for the first time in the positive domain? And in particular, in this case, I'm going to be very explicit in including the origin on the left-hand side. Okay, so I'm going to define the real dynamic cell. This is, you can make the definition the other way around. This is just going to make our life a little bit easier, but genuinely, you won't see that much of a difference. So we need a few things. The thing we're actually going to be looking for is going to be Fn plus. And Fn plus is going to be exactly the question of probability of first entry. So first entry to positive x after n steps. Okay? So this is the question we're asking, and we want to answer that question by being quite clear in how we're actually going to consider our movement on this particular axis. So we're going to have two probability densities. So I have Pn plus and Pn minus of x. And I'm just going to put an infinitesimal quantity here, dx, and you can think of these in terms of being probabilities. I'm an applied mathematician. Bear with me. You can think of them as being probability densities instead if you prefer. Okay, so Pn plus and Pn minus are going to, so notice here to begin with, we're separating already quantities into different parts of the domain, and that's going to be crucial in us solving this problem. So Pn plus is again our probability of, as before, first entry to positive x from negative or 0x at time step n, where we also say that we're landing in the interval x plus dx. Okay? So the probability that I'm somewhere over here, including 0, and that after, at step n, for the first time, I land somewhere in an infinitesimal interval. Okay? Pn minus is going to be my probability of, of being somewhere else in some infinitesimal interval, having not yet visited positive x up to step n. In other words, we have a probability density on one hand that considers arrival into the part of the domain that we're interested in, and we have another probability density that's conditioned on us not having met the condition yet. Okay? And how we've chosen to separate this is very important. Many other separations you could have made in terms of time steps and an initial position of your walker at time n to the next one will give you far more complicated problems to solve. So here is the first part. I know if you work with Wiener-Hopf formulations, many times you have functions that have positive and negative indices in some way. So this is the analogy of that. When we think about these two as being probability densities, we can then say that Pnx plus minus that together is going to be our probability density of not visiting, not having visited, positive x up to step n. Okay. Is that all clear? Good. So, now we actually need to have some definitions. And if we think about these two a little bit, this is the probability density of not having yet visited up to step n, right? Being at some particular infinitesimal location when you land. And so it should hopefully be clear that we could say, well, the quantity we're actually interested in, Fn plus, is just going to be the integral of Pn plus x dx. Okay? And I'm not quite including 0 here because. Okay? Is that clear for everyone? This, in essence, is the quantity we want to find. Any questions of the problem setup? No? Okay. So something that's helpful to notice here is if we think about these two definitions, Pn plus, for example, and the negative side on the left-hand side is going to be 0, right? Because we're conditioning on being at positive x, and this being the first time that happens. And similarly, Pn minus is going to be 0 on the other side. We can then extend it and say that any convolutions of these quantities are also going to collapse. And when we think about this being an evolution process, there are going to be convolutions that will be happening. And so this is a very helpful observation to make early on, that by construction, many of these quantities are going to collapse. Okay? So now we actually get to do some maths. Now we're done with the setting up. So we're going to make them generating functions. Surprise, surprise, I reminded you. So we're going to use them. And we're going to make generating functions for the three things I've introduced. Let's start by having generating functions for probability densities, Pn plus and Pn minus. And I'm going to be a little bit lazy and write them together and in Fourier transform to begin with. But if people want that spelled out, we can do that. So I'm going to have generating functions, so that little squiggly line above anything is going to mean that it's in Fourier space. Okay? And so you can see k there is already in Fourier space, and it's going to be for Pn plus and Pn minus. And that just by the definition of how we said that generating functions work is z to the n Pn plus. Okay, so all that is I've taken the Fourier transform of the probability density here as well. You can ignore that and you just get the definition. So hopefully that's fine. And then we also want the generating function for our first pass probability, which is the thing we're actually trying to calculate. And I'm going to call that capital Phi because I'm very creative. And that is, unsurprisingly, into 0 to infinity, so to the end, we're just going to have the integral like so. Everyone happy with that? Good. Also, is this too small, or can everyone read it? Are we all fine? Okay. Now, what's helpful to notice here is that's the Fourier transform when k is 0. Does everyone see that just by the definition of what that is? So we can write this as the sum from 0 to infinity, set to the m plus of 0, which then very nicely can be rewritten as the generating function. So, yeah. You're smiling. Is there a problem? Yes?
I'm enjoying it.
Good. Good. Okay. Everyone with me so far? Maybe I'm asking that too often. I just want to make sure we're good. Okay. Yes. And so again, like I said before, the convolutions of p's collapse, and when we think of the generating functions, the properties of when those generating functions collapse also are transferable, and we're going to be using that as well. Okay, now we need to think, which is perhaps both more fun and slightly more challenging, but let's actually do it. We're going to write a recurrence relation for these two quantities of how we get from one step to the next. And the idea is very simply, where I am at the next time point depends on where I jumped previously. That's it, right? That's a very sensible thing. So what we're going to say is that at time step n plus 1, p plus of x plus p n plus 1 minus of x, that probability density of me being somewhere, right? That's basically just Pn minus convolved with all the jumps I could have made. Right? So this is where I was at the previous time step, having not yet crossed, and then I can either have crossed or not at the next time step. That's what this is. Right? So we need to convolve somehow with the displacements I can make, which is diverse of p, if you remember, over y, and then we can remember that p and minus is only non-zero for negative values, and so that's going to be from minus infinity to 0. Okay, everyone happy with that? Good. We can write that in Fourier space because this trivially can be extended to all y. On account of it being 0, we can integrate over that with impunity, and so we can say that Pn plus and Pn minus is just the product of Pn minus with our characteristic function. Okay? So this is actually, okay, that's not very helpful, that has color there. I'm sorry, can people read that? Can people read this expression here? Not good. Okay, so this is the first equation that actually matters. This is going to tell us how to proceed from here. I heard a sound. Is that a question or just someone moving because we're human beings?
So what's the lambda again?
So lambda is lambda of k is the Fourier transform of p of x, where p of x is the distribution from which our spatial displacements come. Okay. Any other questions? Okay. That's thinking over for a little bit. I'm going to remove all the definitions because they're very long and they have words, and I much prefer equations.
Before you do that, can I just take?
Yes, you can take as many pages as you like.
Sounds on these indices. First you put Pn minus 1 and it's plus. In the box. Up one.
So Pn plus 1 plus.
Oh, that is plus.
So that's plus and that's minus.
No, in subscript. Subscript plus.
So this is a time step n plus 1, time step n plus 1.
Yeah, then it's consistent.
Yes. Okay, thank you. Good?
Okay. Can I ask a dumb question? So in B at the bottom there,
Yeah.
the second term on the left, yeah. So that one, that 0 to infinity integral, isn't that Fn plus? 0 to infinity Pn from your definition of Fn plus.
Yes, this is
Yeah.
this is my generating function
So
for
that's
Fn
what you're
plus.
taking, yeah. Okay.
Yes.
Just checking.
Yeah, so these are the generating functions for little p's, and this is the generating function for Fn. Thank you for pointing that out. I should have added the extra line. You can put it in here for anyone who just wants that extra reminder. Plus.
If I jump a little bit, just maybe it's stupid, but can we generate the problem when you're interested not on the whole positive semi-axis, but on the finite segment ahead?
Yes.
It's possible.
It is possible. I'm not going to show it here, but there is an extension. You can make further divisions.
It makes sense.
Yeah. Okay. Oh, actually, no. Let's try and do this one. I'm sorry, remove part of the definition. Let's keep that. That's for a little bit. How many for 10 minutes?
It's 2:30.
Good. That works. Oh, there we go. Okay, it doesn't want to go any further. Okay, so what we're going to do is we're going to take equation 1, and we're going to... Actually, does that read in the shade here for anyone? If I do that, can anyone read that? No? Okay. We shall erase that. So choose life. Okay. Erase it. Okay. So, what we're going to do is we're going to sum over n, and we're also, at the same time, going to multiply by z to the power of n plus 1. And I'm going to do that to each side of this so I can get it in the form of a generating function, basically. So that's going to leave me n plus 1. Minus, on one hand, which when I change the indices here to make it consistent, that is going to give me, I'm being a bit fiddly here by still calling it n, but hopefully you see what I'm doing. I'm going to get p plus, plus p minus p0 plus minus p0 minus, and if we really want to, we can put all of them in Fourier space. At the moment, it really doesn't matter. Okay. That's the left-hand side of equation 1. And what we need now is we need to just do the same thing to the right-hand side, and that's going to give us z lambda into...
Probably need to put the bracket a little bit earlier, otherwise it means.
Which bracket?
Just after second chain close. Yeah, just yeah.
Oh, yes, well, yes. If that is meaningless, it doesn't, yes. Thank you.
Isn't there a z? No.
Yes,
No,
you're
no,
right about the
yeah,
bracket,
yeah,
yes, thank
no,
you.
my ex-man.
So what we're going to do is we're now going to have the following. Okay, good. If we impose some initial conditions, and I'm going to just pick one, you have the option of 2, and I'm going to pick for you. I'm going to say that we're going to start on the left-hand side of 0, if you will. So that's going to be 1, and that's going to be 0. So we can rewrite this a little bit. So 1, minus 1. And what we can now do is we can actually notice that this fits with, it's not quite there, we can notice that this fits with the definition of what a generating function is. That in Fourier space. And so what we're going to have is we're going to have plus minus 1 by the definition of what the generating function is. Okay. The same thing on the other side here, we have z lambda into the generating function for p minus, so we have lambda into pi minus. Okay. Is everyone with me so far? all I've done is I've taken my expressions in real space and made them into expressions for the generating functions and picked an initial condition that works. Okay? So we're going to rearrange this a little bit. We're going to get the next equation that's actually one that we're going to be looking at a little bit more. So we're going to have, let's make a little box with it here. That's going to be equal to minus zk into 2 minus z. That's just going to rearrange. Okay. I'm going to put this one too. It's basically the generating function equivalent of the probability density we already have. Here comes the analysis bit, just the bit that I believe some of you are more interested in, is we're going to assume, and it can be shown, although I won't do it because it's a bit too long for what we're going to be doing, although I can give you a reference and we can talk about it after. We're going to assume that these generating functions have no zeros, so that I'm allowed to take the logarithm of them. And there's a series of things we can do to show that it's actually true. But for now, just take that assumption as read and valid. And what we're then going to do is we're going to focus on positive x because our question is first passage into the positive domain. So, what that means is if we take logs, I have, yep, so I have, that's my natural log. I realize that's a little bit unreadable, but that's natural log. Is natural log of phi minus, natural log of 1 minus 7. Okay? I'm going to assume I can do that.
You need to say something about branches.
Yes, so we do need to say something about, and that analysis does exist, but like I said, it's not immediately straightforward. So we can talk about it afterwards. I'm going to skip over here now, but you're going to have to trust me. You cannot trust me in half an hour, okay? So let's look at each of these terms. And let's start with natural log of 1 minus z lambda. If we can expand that very simply, just by taking an expansion. And that is going to give us z to the n over n lambda to the n, which, and I'm going to assume you remember that definition from the beginning of how we can get from the initial Pn, if you remember that, to from n plus 1 is Pn involved with your stepwise, involved with your stepwise distribution. So we're going to use this particular property. And so we can rewrite this as lambda to the n because of our initial condition as minus the sum from 1 to infinity z to the n over n. Yeah. So we do this n times in Fourier space, we get lambda to the n, and that's how the mapping works. Okay. So that bit's fine. We can keep working with that. Good. Now let's have a look at natural log of phi minus. If we think about natural log of phi minus, we write what that actually is. Natural log of phi minus is infinity z to the n minus. That's just what the definition of our generating function is. When we expand this again, like we've done before here, what we're going to get is we're going to get a lot of terms that all take a form that looks like this. So the indices here in n, of course, vary in the minus, but they're all going to be products of p minus. And we're interested in passage to the positive domain. So these are convolutions of p minus full positive x. And as you remember, I reminded you at the beginning that convolving anything of p minus on by construction is going to collapse. So this is going to be 0. And then finally, we have natural log of 1 minus.
According to what you wrote before, you missed the term p tilde 0 in the bottom. No? Log 1 minus z lambda, you put second sum. When you put from lambda tilde to the n, no, above. Next one. The lambda tilde to the n is p tilde n divided by p0 tilde, no? The next one.
So my first
That
one
is
here,
correct.
natural log of 1 is
But
0.
the third.
And when you go from lambda tilde to the n to the pn tilde, you don't need to divide by something.
Pn of 0, no?
Well, Pn of 0 by construction is 1
Oh, I see.
because of the initial condition. But yes, you're absolutely right. We can put in here, in principle, if it makes you better, you're right. Absolutely, in general, you're absolutely right. We need P0, but in this case, it's 1. Well spotted, but not today. Okay, so finally this time, we can again expand like we did up here. And we have 1 to infinity. Like this. I like that you're asking questions. It means you're awake. So this makes me very happy. This term doesn't have any weird convolutions, and that's fine positive x, so we're not going to bother anymore. Okay, so what this tells us, having looked at our 3 terms, is the problem we actually need to address in the positive domain is very simply this one. In other words, we've managed to separate in our expression by the construction of our original probability densities the part of the generating function that concerns the negative domain from the positive one. And so in principle, we have 2 separate expressions we can solve independently. When the conditions become more complex, we add in additional boundaries. So you're interested in passage to a finite boundary in the positive axis, for instance. This is not going to be quite as easily separable, but by construction, you do the same thing and you have more parts that are going to collapse in some way or another. Okay. I see some people writing, so I'm going to leave that. And just talk through what we're going to do now. So this is the final expression that actually is going to be one that we need to do any work with, and that all we have to do now is we have to turn the handle. In other words, we're almost there. What we're going to do is, okay, I'm going to write down here. Can people read down here? How far down can I go? Can I go all the way to the bottom? Who's sitting at the back? Okay, good. So what we're going to do is we're going to take this particular expression and we're going to apply an inverse Fourier transform and integrate over x at the same time. So let me just show you what I mean by that. Inverse Fourier transform and integrate over all x. Minus ikx. Natural log. And I'm going to be explicit here on the dependence because we need to notice something. So x. Okay, that's what we're going to do. And then we're going to recall again the properties about the collapsed or positive or negative domain. So in principle, this can be extended. And because we can extend this domain, we can also swap the order of the integration. So we're going to do that. So that's going to give us 1 over 2 pi double integral into ikx natural log and 1 minus I plus. Okay. This, if you stare at it for a little bit, we can hopefully convince ourselves is the natural log of 1 minus 5 plus when k is 0. And now we're almost home because, oh, sorry, when k is 0. This, when k is 0, if you remember what, I'm going to write it again because it's not here, but if you remember we wrote that this generating function here was related to 5 plus when k is equal 0. Let me just double check some. Yeah. This is exactly that. We showed that earlier. I'm just reminding you Oh, sorry. This has the generating function of that. It's not quite equal to that. So this is going to be your generating function of that particular quantity. In other words, this is natural log 1 minus up to 5 plus. So we have our, in generating function space, this is the exact same quantity that we showed that we were interested in to begin with.
That is not completely visible.
I will rewrite it.
Yeah,
then.
could you write
The lowest.
log 1?
The second bolt, the lower bolt.
Yeah.
Just
Yeah.
other
Are
one.
you saying you want me to do
Temporary.
a switcheroo?
Ah, that also works.
Yeah, and that is a little bit. Yeah.
Oh, okay,
Just
that's
for-
an e to the minus x.
Just for a minute.
Yes. Up high so everyone can see it. Okay, so again, that's the generating function of the quantity we're interested in. And we can do the same thing to our right-hand side, natural log of 1 minus z to the lambda. We did the expansion for that. We know it's related to the probability. And so I'm just going to keep working up there. Advantages of being tall. Plus infinity. Over 2 pi. Minus ikx. And then we have our sum. Z to the n, over n, Pn, okay. And we can show now that that's so over n, that's just the inverse Fourier transform of this particular quantity, so it's just our integral at the end of the day of my probability of being anywhere on the real line, integrated over positive x. So this quantity here, I'm just going to call it Cn, that's my probability at any given time step of being in the positive domain. So that's not quite being there for the first time, it's just in general at any time step the probability of being there. Okay, so it's a more general statement. And if we assume we have a symmetric stochastic process, then that probability we're going to make a half. We can make that more complex, we can make it depend on n. For now, let's just make it half. You're looking at me like you want me to make it more general. We can do after if you want. Okay, so if we do that and we combine, so remember that's our left-hand side, and that's our right-hand side, we can combine them and we get this beautiful expression. We're going to get, there we go, that's good. We get 5 plus, so I'm just combining them and rearranging them a little bit. It's 1 minus the exponential of minus sum from 1 to infinity z to the n over n. And this is where Cn would be, and I'm just making that half. Yes?
It's something simple.
Hmm?
It's something simple. I mean, this sum could be summarized.
Yeah, it can. And that, you're right. Okay. What we can then do is we can remember this is the generating function of z to the n. This is the generating function, so let's remember what that means. 0 to infinity, z to the n, fn plus. Right? So all we have to do now is we expand that, we do a Taylor expansion of that, and we match the terms to fn. And that's our answer. And I'm not going to do that because I believe that you all have the ability to do Taylor expansions. So I'm just going to tell you that the answer at the end is that fn plus goes like n to the minus 3 halves. You have to use Taylor's approximation, but I believe in your ability to expand square roots. So, that's it. I have a little spiel on the screen that I can pull up in a minute if you're... Is anyone copying this or writing it? Yes, you have a question.
Is this somehow related to Spitzer's identity?
In some way, yes. I couldn't tell you exactly how, but yes. There are whole slews of books on probability and statistics and how these things are related, and in fact I have some references at the end, so maybe I should just pull those up so you can have a look. But Anastasia, oh, okay. Maybe I have to do one of these. Pull it down. And then the screen will magically come back, you promise me, Anastasia. Now, if it doesn't, I will be very sad and I will cry.
Oh, you just hidden the last line, the conclusion.
I've just hit, okay, well.
Just for a second.
Yes, for a second, for a
Just the
second.
last line.
It's hidden.
So, IN plus, you cannot recover it explicitly?
You
or-
can. You can.
Or you just put it like it behaves,
Yes.
but it's more complicated.
Yes. You can write it as a summand of gamma of fractions of gamma functions, and that will be the full complete answer that you can get. As an applied mathematician, this is the part that gives me the intuition. So it's 1 over n to the 3 halves.
Because then goes to infinity.
Yeah. But it will apply, if you test it, it holds very, very close to n to 1 and 2. So
Is there any sort of physical intuition
There
as to
is.
why it goes up 1 over to the 3 over 2? It's not immediately obvious.
there is, but I'm not sure I want to be that person who goes into universality laws. I stopped being a physicist in 2015. No, so it's, if you look at first passage problems, 1 over n to the 3 halves is, if nothing else, a tail that comes up very often in these things. And there are all sorts of speculations as to how and why this happens. I have yet to find one that's convincing always. In particular, when you add in curious boundary conditions or what the transition threshold is it in a bounded region rather than just positive x? It's not quite as simple, but it's an answer that comes very often. Now, Anastasia, I'm going to cry.
I'll cry with you.
You'll cry with me.
Push it up again.
Push it up and down.
Up and down again.
Alright, the classic switch it off and on again.
It's photosensitive, so.
Is it
The
Ah.
yes.
I've rambled too long and it's gone to sleep.
Okay.
Yes, yes, it's my fault. I'm sorry, Anastasia. Oh, but I have to spell.
Just hit
Enter.
Yes, good. Okay. So hopefully I've convinced you of some, if not more, of the following. For those of you who do Wiener-Hopf, hopefully you've seen a few, if not many, similarities between what's been going on here and the methodology you use. If not, then this is just a very simple way of starting to think about stochasticity and how it can be applied. So, two obvious ones is when is the first time a signal actually goes through a network if you're trying to model the brain, or when is the first time you make a certain amount of money out of your investment, what's the probability of that? And hopefully you can think of many other examples of how and when this applies. I gave you some examples earlier. And genuinely, the way you apply this is very free to how you apply it and the systems you choose to work with. The downside of that is there are thousands of us who work on this, and some of us are more applied, and some of us are more pure, and some of us are in between, which means that we don't always all speak the same language when trying to solve the same problem. But hopefully, you now understand my language a little bit better. We can start from there, but please pester me with questions. Like I said at the beginning, I love questions. And if I can't answer your questions, then maybe some of these can. And that's it. Thank you.
Thank you very much, Helena. Do we have any questions from the audience?
I've not really seen a factorization. That's why I was referring to Spitzer's work, where I really see a nice factorization process relating to the work of Dexter. But here I have not really those. I may have missed it.
Can you rephrase your question?
Where's this factorization property? I see it from a very algebraic point of view, and so in Spitzer's work, there is a nice way of factorizing in terms of positive max or min part, etc. Is this as well here the case?
Not directly here, no. When you get to more So I think I mentioned at the beginning, if you're working more formally with a family of processes, like Levy processes, where you just assume particular properties of the functions, then yes, it does appear more formally. I think Brianna is probably the person to go to see more examples of the factorizations of the kinds you're looking for applied to these problems, but it's not directly here.
So yeah, I mean that's what I think lots of the Wiener-Hopfers amongst the audience will think, that the crucial part is we have some stuff which relates to the physics of the problem. We have to decompose that into a product split, and so it's trying to work out here where, as you make the the Levy processes more complex, where that factorization appears here and how and where the work is to do that.
So the work comes. So in some sense, the split comes a priori in how you define it. So here, the closest you get to that split is, I started out by saying I have this Pn plus and Pn minus, which is, by construction, these probability densities that tell you first passage from which part of the domain you're in. And so if you're interested in a problem where this passage can happen multiple times, and you're looking at a bounded variation problem where you could have one bound and not the other, for instance, then you have to work a lot harder to find and actually enable that factorization to happen, which is why I'm pointing towards some of the more formal Levy process stuff. In the more simple cases, you can do it by construction.
So the equation that you labeled 2 and you got that thing, in this case, was simple enough that you could.
Yes. So this is
in general that would be much more complicated.
Yes. Yes. So what I was given to understand is that most people, at least from what you said at the beginning, don't come from a stochastic process background. So what I was genuinely hoping to do was to start with one of the simplest ways that one can start tackling stochastic problems, which is Sparr-Arness's theorem from 54. And if you go and you look at, particularly Feller, I imagine, is we're going to appeal to more people. The next step in that direction will have analysis on branching. It will have specific details on when you can do the factorization and how you do it. But what I was partly hoping to do here today as well was actually to give a common language, because, like I said as well, the language is not common despite the fact that we're trying to solve the same problem in very different ways. Yeah. For those of you who want to go and look through this particular calculation, I've made an effort. I don't know how many people are master's or PhD students in the room. Maybe none at all. But the very, very first step into it is the first step in Random Walks, which has the more modern notation, so that should be easy to follow as well. Yeah?
I use these techniques in a non-commutative setup.
Yeah.
In a very different realm. But can you do these things? What do people in this context do when they have to face, say, matrix valued Lévy processes, such things? How do you deal with such things?
Carefully. You make assumptions about the properties of the process such that a separation can be made. So if you think of a particular stochastic process and you have it in matrix form, you try and define the properties of the stochastic system in such a way that the matrix could be reducible or could be treated in ways that are better known. So basically you try to make it into not a matrix and work from there.
Is this because of the lack of understanding how to handle the really non-commutative part?
At least as far as I know. The matrices, when high dimensionality in stochastic processes, when you have non-commutative behavior, is
I'm asking because there's a non-commutative version of Spitzer's identity. And so this means, in principle, this has been solved, or in general, to deal with the non-commutative setup.
In principle, yes. How far you can actually take that into a real problem that has more complex processes, then that's, as far as I know, that's not as well known. You may have a general formulation for how a family of processes work, but maybe your assumptions, particularly when you're dealing with linear processes, you're assuming that there is a particular family of properties or that these systems have, and maybe your condition is very strong, and perhaps the condition can be relaxed slightly. But a general problem when you're looking at the literature is you will have conditions that are comparable, but they're not the same. And so not all of the results and conclusions that you may have will transfer directly.
I have a elementary question. So you can also do this in continuous time?
Oh yeah, absolutely. Absolutely.
Just backward for one equation to solve it?
Oh yeah, there are many ways of even solving this problem. This is just the way that if you're trying to start a conversation about Wiener-Hopf and its applications to stochastic processes, most easily lends itself to analogy. But yes, you're right. There are ways of solving it. You can solve it in continuous time. You're absolutely right. This is not the forefront of what we can do with these problems. But at least I was hoping that it would be an illustrative example for those who are curious.
Well, if there are no further questions from the audience, last chance.
Yes, maybe.
Well, we do have interest of time, sorry, it's 3 p.m., so perhaps we can discuss these
Rhetorical
afterwards.
question.
So let's thank the speaker once more.
That's mean. You can't ask for